Hello everyone, welcome to section 7.3. What we're going to learn in this video is a new set of formula that turn out to be super useful in calculus. We're talking about the double angle, the power reducing, and the half angle formulas. We'll actually find that these formulas are just a direct consequence of the addition formulas that we learned in 7.2. Now while we go through some exercises and start working with these formulas, you may not see why they're so useful now, but I promise you when you get to calculus, or really just in any future math class, these formulas pop up all over the place. So let's get started. What we're going to do first is we're going to derive these formulas. Okay, so let's first do the double angle formula for sine. Okay, so the sine, here I'm going to be using x's and y's. The book likes to use x's and y's. I think in the previous videos I was using thetas and phis. Let's use x's and y's. So sine of x plus y, okay, remembering that sine is a very friendly function. Sine of x, cosine of y, likes to follow the rules. And here we have it. Here's the addition formula for sine. If I want to know the double angle, here we're kind of thinking of these x's and y's as being angles. Well, what if we replace y with x, or make these be identical angles? So what if we do sine of x plus x? So we'd be rotating an angle x and then rotating that same angle x again. Okay, what would the formula look like? Well, wherever I see a y, I'm going to replace them with x's. So we'll get the sine of x times the cosine of x plus the sine of x times the cosine of x. So what we have is that the sine of 2x, x plus x is 2x, is going to be equal to, well, I got a sine of x times cosine of x plus another sine of x cosine of x. We have two of those. So we get 2 sine of x cosine of x. And here is the double angle formula for sine. Again, notice the character of sine. Sine is such a friendly function. It likes everyone to be together. It's very friendly. It's sometimes a little bit shy, but look, it's got a sine and a cosine. And even though oftentimes cosine is kind of, pushing sine to the back burner, sine is very friendly. Sine says, hey, it's okay, cosine. It's okay, you can still hang out with us. Okay, so here is the double angle formula for sine. Okay, let's write that up here, and let's drive the other ones. So here we have the sine of 2x is equal to 2 sine of x cosine of x. Okay, let's do the same thing with cosine. Okay, so let's think about the addition formula for cosine. Remembering that cosine frickin' loves itself, and it's a little bit of a rebel. Cosine says me, 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 me. Cosine x, cosine y. I don't like to follow the rules. You say plus, I say minus. Sine of x, sine of y. It's like, come on. Sine was so friendly to you. Cosine, why you gotta put sine on the back burner like that? Okay. So what if we replace the y's with x's? What if we have cosine of x plus x? Well, get cosine of x, a cosine of x, minus sine of x times sine of x. Just replacing all our y's with x's. And let's see what we get. Well, we'll get that cosine of 2x is equal to, looks like we'll get a cosine squared of x minus sine squared of x. And again, we see the character of cosine. Cosine says, me, 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 me first. Sine, sine, you gotta go second. Cosine, you're so selfish. Okay. Not only is cosine really showing its true colors here, but cosine is very selfish. Cosine doesn't just want one formula. It doesn't want to be like, so sine has one formula. Cosine says, well, I don't want just 2 formulas. I want 3 formulas. Come on, cosine. There's actually 2 alternative formulas for the double angle formula for cosine. Cosine squared of x minus sine squared of x. Okay. The other two formulas come from just using the Pythagorean identity. So let's get the other two for cosine of 2x. So we know, or I hope we know, that sine squared plus cosine squared is 1. So we have that cosine squared of x would be equivalent to 1 minus sine squared of x. Or, similarly, that sine squared of x is equivalent to 1 minus cosine squared of x. Okay, so I'll erase this piece right here. So we're just going to make those replacements into the double angle formula for cosine. So instead of the one we have here, I don't know, how about we replace one with cosine first? So this would be the same thing as a 1 minus sine squared of x, just replacing cosine squared with 1 minus sine squared, minus a sine squared of x. So we have a 1 minus, looks like we'll get a 1 minus, well, these parentheses aren't doing anything. I'll have a minus sine squared, another minus sine squared, so we get a minus 2 sine squared of x. And here is another version of the double angle formula for cosine. So let's go ahead and write this up here. 1 minus 2 sine squared of x. Okay. So now the other version of the formula comes from just making the replacement with sine squared. So you can either make the replacement here or you can make the replacement here. Doesn't matter. Let's do it with this bottom one. 1 minus 2. Let's replace sine squared with a 1 minus cosine squared of x. So we will distribute it in the negative 2 into the parentheses. So we'll get a 1 minus 2 plus a 2 cosine squared of x. Or how about we write this as this is what, a negative 1 plus 2 cosine squared of x. Or, I usually don't like to write a negative 1 plus. How about we write this as a 2 cosine squared of x, then minus 1. I'm really just flipping the order of addition here. Okay, so let's write that here. So we get a 2 cosine squared of x minus 1. And again, cosine shows its true colors. I guess the one thing that's nice about the cosine formula is there's a formula that involves cosines and sines. There's a version of it that just has sines in it, and there's a version that has cosines in it. Well, if they have both cosine and sine, cosine is very selfish. Cosine goes first, sine gets pushed to the back burner. Well, if there's no cosine involved, cosine says, pff, pff, if I'm not here, then, get out of here. Get out of here. But of course, if cosine's involved and sine's not there, it's like, oh, me first, me first, me first, me first. Okay, so here are the double angle formulas for sine and cosine. There's just one formula for sine, and there are 3 formulas for cosine. Okay, there's also a double angle formula for tangent. Okay, tangent of x plus y. Okay, if you forget this one, we can always look at the back of our trusty textbook. You'll see here that we have all of our double angle formulas here. Now, it's nice to have these memorized. Specifically, I'm going to say it's nice to have the double angle formulas for sine and cosine memorized. I'll talk about here in a second that I don't really have this one memorized, or oftentimes I don't know, I just don't use it too often. I'll show you why in a second. But let's go ahead and just derive it really quickly. So tangent of x plus y, and again, if you forget what the sum formula for tangent is, we can just look it up. So I think it's the tangent of x plus the tangent of y all over a 1 minus the tangent of x tangent of y. Again, this is in the back of the textbook. Okay, so let's just make that replacement with an x plus an x. So replacing y's with x's, we'll get the tan of x plus the tan of x all over a 1 minus the tan of x times the tan of x. So we'll get a 2 tan of x all over a 1 minus the tan squared of x. And here is the double angle formula for tangent. Let's write that up. Let's write that up here. So this would be, of course, the same thing as tangent of 2x. So let's write that right here for completeness. We have that the tangent of 2x is equivalent to 2 tan of x all over a 1 minus tan squared of x. Okay, now to be honest, I mean, sometimes this formula is useful to use, but if I'm in a pinch and I need to know what tangent of 2x is, well, I can always do sine of 2x all over cosine of 2x. I'm usually always remembering that tangent is the same as sine over cosine. So again, if I forget this, I'm always kind of going back to the bread and butter of tangent, sine over cosine. Okay, now out of all these formulas that I have right here, what are the ones that pop up the most? I'm gonna write them in green, because these are important. They come up all the time, and I highly recommend you commit these to memory. Okay. So let's get practice with working with these. Let's do some exercises. Okay. Our first exercise, or how about our first example, is let's say we're given that sine of x is equal to 4/5, and x, here we're thinking about x being an angle, and x is in, let's say, quadrant 2. We want to find sine of 2x, cosine of 2x, and tangent of 2x. This is what we want to find here. Go ahead and pause the video and give this problem a shot on your own before we do it together. Okay, let's do it. I think the easiest one to find here is going to be the cosine of 2x. So I'm actually going to start with cosine of 2x. You don't have to start with cosine of 2x, but what's nice about cosine of 2x is it does have 3 formulas. There's one that has sine and cosine in it. There's one that has just sine in it. There's one that just has cosine in it. Well, if I was just having to find cosine of 2x and maybe not having to find sine of 2x or tangent of 2x, well, since I know what sine of x is, I'm going to use the formula. For cosine of 2x that has a sine in it. So that version is a 1 minus 2 times the sine squared of x. Now we can just, a little plugging and chugging. 1 minus 2. Okay, we'll replace sine with 4/5, and we're squaring that. So we have a 1 minus a 2. 4/5 squared is what? 16/25. Okay, we'll need to add these fractions. So this will be a 1 minus 2 times 16, we're at 32 over 25. Instead of a 1, let's write that as a 25 over 25. Okay, so now we need to do 25 minus 32, which is what? -7. So this will be -7 over 25. So let's write that over here. We just figured out that the cosine of 2x is equal to -7 over 25. Okay. Let's go ahead and find sine of 2x. Sine of 2x, okay, sine is friendly. It's 2 sine of x, cosine of x. Okay, so there's no alternative formula, unfortunately, for sine of 2x. So we're stuck with having to figure out what cosine of x is. We know what sine of x is. We don't know what cosine of x is. What are we going to do? We're going to draw a triangle. You can either draw a triangle or use a Pythagorean identity. I'm just going to draw a triangle. Okay, so we have an angle x. So we're saying this is the angle x. And sine is 4/5, and sine is opposite over hypotenuse. So we would just need to find the adjacent side of this triangle. You could use the Pythagorean theorem, or this is a 3, 4, 5 triangle, so we know this here would be 3. Again, you could use the Pythagorean theorem if you didn't know this. Okay, so we have that sine of x is 4/5, but specifically, we want to know what cosine of x is. What is cosine of x? Well, cosine is adjacent over hypotenuse, and this will be 3/5. Now, we need to be a little bit careful here. We need to be careful because we need to remember that x is in quadrant 2. Whenever I draw triangles and I'm doing these type of exercises, I usually ignore what quadrant it is at first. I draw the triangle as if we're in quadrant 1, as if we were in quadrant 1, and then at the very end I adjust the sign. Okay, so since we're in quadrant 2, cosine is negative there, so cosine of x is negative 3/5. Now, if you decide to use a Pythagorean identity here instead of drawing the triangle, you could have done that also. You could have recalled that sine squared plus cosine squared is equal to 1. Or you could recall that cosine squared of x is equivalent to 1 minus sine squared of x. So we get that cosine squared of x is equal to 1 minus 4/5 squared. So that'd be what? 1 minus, what is that? 16/25. How about we replace this 1 with a 25 over 25? Okay, 25 minus 16, what is that? 9/25. So we have the cosine squared. Cosine squared of x is equal to 9/25. We could square root both sides, but we'd have to remember there's a plus or minus. So you'd have that cosine of x would be equal to the plus or minus 3/5, but now we have to choose the plus or minus. Here you would say, okay, well, x is in quadrant 2, cosine is negative in quadrant 2, so you would record the negative. So really, when you're using the Pythagorean identities, you're really secretly just doing a right triangle exercise and using the Pythagorean theorem behind the scenes. Or that the triangle is really what's going on behind the scenes. So either way, it would work. Okay. So now if you want to know what sine of 2x is, now it's all just plug and chug. Okay, so we'd get 2 sine of x. Sine of x is 4/5. And cosine of x is negative 3/5. So what are we going to get here? Well, we'll get 2 times 4, what is that? 8. 8 and 3. 8 times 3 is, what, negative 20. 8 times negative 3 will be negative 24 over 25. So here we have sine of 2x is negative 24/25. So I'll write that right here. Sine of 2x is equal to negative 24 over 25. Okay. Okay, so now we need to figure out tangent of 2x. And maybe it was good to keep that triangle up. We had that triangle up here a second ago. Let's keep it up. So we knew sine was 4/5, and this would have to be 3. This is the triangle we drew. Again, I'm imagining it in quadrant 1. Okay, so you have 2 options to figure out tangent of 2x. You could use that formula. However, why use that formula when I know what sine and cosine of 2x are? So one option, if you want to figure out what tangent of 2x is, and you already know what sine and cosine of 2x is, you could just do this. Okay, so putting that together, what are we going to get? Well, sine of 2x, what is that? That's negative 24 over 25 all over, let's see, cosine of 2x, that would be negative 7/25. Okay, so this is the same thing as negative 24 over 25 times a negative 25 over 7. Looks like these 25s cancel, and we're left with, well, I have a negative and a negative, so that's a positive, so it looks like we're going to get a positive 24/7. So we have that the tangent of 2x is equal to 24/7. I think this is the easiest way to do this problem, but again, you could always just use the double angle formula for tangent. Okay, if you forget what it is, use your trusty textbook, look in the back. Let's, I think it's what? It's 2 times the tangent of x. The only reason I know this is because I just wrote it on the board. 1 minus tan squared of x. Okay, let's just use the formula and verify we get the same answer. Okay, well, looking at our triangle, we have that the tangent of x would be 4/3. But we have to be careful here. We're in quadrant 2. If we're in quadrant 2, remember, tangent is negative in quadrant 2. So we need to put a negative here. Let's see. Sine is positive in quadrant 2. Cosine is negative in quadrant 2. So tangent is sine over cosine. One's positive, one's negative. That means tangent's a negative there. Or you could think of the slope of the line in quadrant 2 if that's a negative slope there. Okay, so tangent of x is negative 4/5. Okay, let's just plug it into this formula. So we'll get 2 times what? A negative 4/3 all over a 1 minus a negative 4/3 squared. So what are we going to get here? Looks like we're going to get what? A negative 8/3. A negative 8/3 all over, what is this going to be? This is going to be a 1 minus what, a 16/9. So we get what, a negative 8/3. Think of this 1 as about a 9 over 9. A 9 over 9. Okay, 9 minus 16 was at negative 7. So we're going to get a negative 7, a negative 7/9. So I'm going to kind of bring this up over here. So what do we have? We have negative 8/3 divided by negative 7/9. So that'll be times negative 9/7. Okay, let's think here. Well, 9 is 3 times 3, so this 3 will cancel with a 3 in the 9. So 3 times 8 is 24. Negative and negative make a positive. We have a 7 in the bottom. And we got the same answer. Okay, in my opinion, what was easier? I think it was easier since we already knew what sine and cosine of 2x were. It was a lot easier for us to figure out tangent of 2x. However, if the problem just says, hey, given that sine is this, find tangent of 2x, maybe it would have been a little bit quicker to just use the formula right off the bat. So it kind of depends on the situation. But here's the answer to the problem. Cool. All right, let's do some other exercises. Okay. Let's try to evaluate how about cosine of 2 times the tan inverse of how about 12/5. Okay. We want to evaluate this without a calculator. Okay. Go ahead and pause the video. Pause the video and give this a shot on your own before we do it together. Okay, let's do it. The key thing to realize here, whenever you see a tan inverse, what do any inverse functions do? They eat ratios and spit out angles. Inverse trig functions are angles. Here, the first thing to realize is, well, tan inverse, this is some sort of angle. So what we have here is we have that theta is equal to the tan inverse of 12/5. Okay, so we have that tangent of theta is equal to 12/5. Okay, now ask yourself the question, what quadrant is theta in? What quadrant is theta in? It has to be in quadrant 1. Why? Because tan inverse spits out angles. Tan inverse spits out angles between negative pi over 2 and pi over 2. Well, tangent is positive in the first quadrant. So theta must be in the first quadrant. So this means that theta is in Q1. It's good to know. All right, so really what we have to do here, what we're trying to figure out, is we're trying to figure out cosine of 2 theta. So it's really kind of up to us on which formula we want to use for the cosine of 2 theta. Okay. How about we do the one that has both cosines and sines in it? So that's cosine squared of x minus sine squared of x. Remember, cosine loves itself. It's always pushing sine away. Okay, so we just need to figure out what cosine of x is and what sine of x is. Well, we can get that all from this information right here. This tan inverse of 12/15 is whispering us sweet little nothings about the triangle. It's whispering to us sweet little nothings about this triangle. Or it's whispering us sweet little somethings about that triangle. Okay. I should have put thetas here. Okay. So here's theta. Okay. Tangent. This would be 12 and a 5, so it's opposite over adjacent. Okay, we need to figure out the hypotenuse. Okay, so the hypotenuse will be what? The square root of 12 squared plus 25 squared. So what is that? 12 squared is 144. I put 25. I already was squaring it in my head. 5 squared, which is 25. So what's that? That's the square root of, what will that be? 169, which I believe is 13. So the hypotenuse will be 13. Okay, go ahead and erase what I have here. Okay, well, I hope you see that cosine of theta is what going to be? Cosine of theta is going to be 5/13. And sine of theta is going to be 12/13. Okay, so what are we going to get here? So we're going to get 5/13 squared minus 12/13 squared. Let's see what we get. So we'll get what? 25 over 169 minus 144 over 169. So what? 25 minus 144, 25 minus 144, it's negative 119. Negative 119. That's what my notes say. Let's double check. Subtracting is hard. Negative 119 all over 169, which is the answer. Okay, for fun, how about we do this problem with a different version of the double angle formula for cosine, just to see that we're going to get the same thing. Just a fun exercise. Okay. Well, what if we do the one with, I don't know, how about we do the one with cosines? So what? 2 cosine squared of theta minus 1. Okay. So what are we going to get here? This is 2. Well, cosine is 5/13. Okay, minus 1. So what are we going to get? We're going to get 2 times 25 for 169 minus 1. How about instead of a 1, how about we write a 169 over 169? So what do we get here? We're going to get 50 over 169 minus 169 over 169. 50 minus 169, that's negative 119 over 169. That deserves a smiley face. There we go. For a fun exercise, show that you would get the same answer if you did the other version of the double angle formula for cosine. That'd be a good exercise for you to try. Cool. All right. Let's do one more. One more of this flavor, at least. How about evaluate, how about cosecant of 2 times the sine inverse of 2/3. Ooh, a little spicy. Ooh, juicy. All right, pause the video and give this a shot on your own before we do it together. Okay, let's do it. So what we're going to realize here is inverse functions, inverse trig functions spit out angles. So right off the bat, this is telling us that theta is equal to sine inverse of 2/3. So we have sine of theta would be equal to 2/3. Okay. Again, you should convince yourself that we're in quadrant 1. All right, so what do we have to figure out? We're trying to figure out what is cosecant of 2 theta. Well, notice here that we actually don't have a formula for a double angle of cosecant. But that's okay, because we're just going to use the reciprocal identity. This is equivalent to 1 over the sine of 2 theta. And now we can just use the double angle formula for sine. This is 1 all over 2 sine of theta cosine of theta. So now we just need to know what sine and cosine of theta are. Well, we already know what sine of theta is. We need to figure out what cosine of theta is. So let's draw a triangle. Okay, 2/3, so 2 and a 3. Sine is opposite over hypotenuse. Okay, we need to figure out what this length here will be, and I think that's going to be the square root of what? 3 squared minus 2 squared if we're using the Pythagorean theorem. So what is this? This is the square root of what? That's 9. 9 minus 4. This will be root 5. So let's put that right here. So here we have root 5. Okay, so we need to figure out what cosine of theta is. Well, cosine of theta will be adjacent over hypotenuse, so that's root 5 all over 3. And now it's all just about plugging and chugging. 1 all over 2. Let's see, sine of theta is 2/3. And cosine of theta is the square root of 5/3. Okay, let's clean this up. Bring our work over here. So it looks like we have a 1 all over, what are we going to get? We're going to get 4 times root 5 all over 3 times 3, what is that? That's 9. So now we're just going to reciprocate, so this is the same thing as 9 all over 4 root 5. Now I'm totally fine with this answer. It's going to be very common though that the book's going to have the denominator rationalized. So how about we hit this with a root 5 all over a root 5. So we'll get 9 times root 5. 9 times root 5 all over. We're going to get a 4 times root 5 squared. Root 5 squared is 5, so we get 4 times 5. We're going to get out 20. So here is our answer. Okay, let's take a look at this next example. What we want to do is we want to express this trig expression in terms of trig functions only. Go ahead and pause the video and give this a shot on your own. Okay, let's do it. This isn't too much different than the type of exercise we were doing before this one, except now there's just x's in it. Again, what we should realize is that inverse trig functions spit out angles. So what we're trying to figure out is what is the cosine of 2 theta. Okay, and specifically, we know that theta, maybe I'll write it up here, that theta is equal to the tan inverse of x over 3. So we have that the tangent of theta is equal to x over 3. Let's go ahead and draw our triangle. Why do we need to draw a triangle here? Well, thinking about the formulas, the 3 different formulas for the double angle formula of cosine, well, I need to either know what sine of theta is or cosine of theta is. Now, which formula you use here is completely up to you. Let's use, I don't know. Let's do the one with both of them. Cosine squared of theta minus sine squared of theta. If we're already drawing a triangle, it's pretty easy to figure out both of these. Okay, so here's theta. So this will be x and this will be 3, opposite and adjacent. Okay, the hypotenuse will be the square root of x squared plus 3 squared, or this will be x squared plus 9. So we'll have that the cosine of theta will be 3 all over the square root of x squared plus 9. And we'll have that the sine of theta will be equal to x all over the square root of x squared plus 9. So plugging everything, cosine squared, so we're going to get a 3 over the square root of x squared plus 9 squared minus, we'll have a x all over the square root of x squared plus 9 quantity squared. Okay, so what are we going to get? When we square this, we're going to get a 9. This square will kill the square root. Minus, we'll get a x squared all over an x squared plus 9. We have a common denominator. We can subtract their numerators. So 9 minus x squared all over x squared plus 9. And this is the answer. This is the answer. Okay, you should get the identical answer if you used a different version of cosine of 2 theta. Maybe let's just do one for fun. We'll show we'll get the same thing if we use a different version of it. I don't know. Let's use the one with, I don't know, we could use the one with cosine. How about 2 cosine squared of theta minus 1? It's another version of the formula. Show we'll get the same thing. So we'll get a 2. Well, cosine squared will be what? A 9 over an x squared plus 9 minus 1. Okay, so this will be what? An 18 over x squared plus 9. Let's make this 1 be a x squared plus 9 all over x squared plus 9, so we have a common denominator. Okay. So we'll have a 18, an 18 minus, don't forget the parentheses, x squared plus 9 all over x squared plus 9. Distribute in that minus sign. We'll get an 18 minus x squared minus 9 all over x squared plus 9. So it looks like we're going to get out a 9 minus x squared all over x squared plus 9, which is the exact same answer we had when we used the version where it was cosine squared minus sine squared. A great exercise is do this problem again using what 1 minus 2 sine squared of theta for the cosine of 2 theta. Either way, you will get the same answer. This is fun. This is fun. Okay, that's all I have for working specifically with the double angle formulas. What we're going to do in the next video is we're going to talk about the power reducing formulas. We'll see you there. Take care.